So welcome, and thank you to the entire emBO team for organizing this conference. It is always an honor to be a presenter, and it's been wonderful to chat with our friends and colleagues and meet new developers. We're here in San Francisco, but we just wish that we could all be in Bochum. I'm Barbara, and this is Ansel, and welcome to our talk about modern C++ from the beginning to the middle. So the majority of this talk is going to focus on parameter passing. But in order to do this, we need to go back to the beginning and establish some definitions about data types. We're also going to need to cover value categories and expressions. We need the clicker. So, Ansel and I are the co-founders of the CopperSpice project. And CopperSpice is a set of cross-platform GUI libraries. All of our work is open source and everything is available on GitHub. And in addition to CopperSpice, DoxyPress is an application that we've produced and we've written. And what DoxyPress is it takes your source code and your comments, and it will correlate that together and generate documentation. DoxyPress also can take various other languages and you can pick various outputs. The other three libraries that you can see here on the screen, these are all standalone libraries, and they can be used in any C++ application. These libraries happen to be ones that we use internally in CopperSpice.
So let's start with data types. So what makes something a data type? Could you define a data type? How do data types relate to expressions? Does any of this matter? Will it affect the way you write code? Can you pass a pointer by reference, and is it even meaningful? Do we need references in the language? And if I say the word reference versus L-value reference, did I just say the same thing 3 times, or do they have different meanings? We're going to start with C++11 here because it was a new beginning for the language. It defined new data types, it added new value categories, and we got new functionality like constexpr, lambda expressions, and smart pointers. There's been a lot added since C++11, but everything we show in this talk is going to be from the 11 timeframe. A few of these things changed slightly in later revisions. As you can see, the standard has gotten much larger, although you can't compare these numbers directly because they changed the page size and shrunk the font in the last revision.
So let's start by talking about the definition of a data type. What a data type is it's defined by 2 characteristics: a set of possible values and the operations which can be done on or with these values. So if I was trying to learn a foreign language, maybe like learning to speak German, I would actually want to focus on vocabulary. There's a lot of other things I would need to learn and to speak German well. But the first thing I need is vocabulary. That way I can put everything together later and have somebody help me with the sentence structure. But a data type in a computer language, this is like the vocabulary for a spoken language. So we need to really look at data types in order to understand what C++ really is, or in fact, any computer language.
The data types in a language are broken down into a bunch of groups. And the first group is the primitive or the simple data types. These are the really fundamental types which have to be part of the language. And they're single valued, which means, for example, if you have a double variable, it contains a single number. It doesn't contain multiple numbers. It can only have one value at a time. Then we have the built-in data types. And this is a category that means this type is provided by the language. Obviously, the types in this group will vary depending upon the programming language. So for example, in C++, we have std vector. It is definitely built in. It's provided as part of the standard library. But it's built out of smaller basic data types. There's another group, which is the composite or the compound data types. And these are the way you derive a new data type from some other group of primitive or built-in types. And when you create a composite type, you're producing a new data type. The most common ways to do this in C++ is by using a class or a structure. This is a way to compose a new data type and construct one out of other, more basic data types. There's also the idea of user-defined data types. And this is any data type that is declared by you, the developer, in your source code, or it's declared by some third-party library. It's not provided as part of the standard. So in C++, anytime you declare an enum, that's declaring a new data type. Also, anytime you declare a class or you use a class from some third-party library, that's also a user-defined data type, as well as being a compound data type.
The next one that we have is an abstract data type. And this is a type which does not specify an implementation. Let's look at a stack. If we look at the functions push and pop, these are well defined in computer science. But the implementation of a stack, that will depend on the storage container. The idea of an abstract data type is that the developer should actually inherit from the abstract data type, complete or finish or change any implementations that you need. So when you instantiate it, you are actually instantiating your user-defined class that you've inherited from this abstract data type. So an abstract data type is not meant that you create one of those. Now we're going to talk about a pointer data type. So when we defined a data type, we talked about the fact that a data type by definition needs values and operations. So the values for a pointer data type, a null pointer, or the address where some data is located. These are the operations that you could do with or about the actual values for the pointer. Most of these sound very familiar. You can dereference a pointer and you could compare pointers. So this is the complete list of what you can do with this data type. Let's take a look at an example of a pointer data type. In order to declare a pointer, we need to know the type and we need to have a star. And if you look at the in star var1, that's our variable, declares a pointer to a value of type int.
Then on var2, we're declaring a pointer to a widget. Since the size of the pointer type just depends on the platform, var1 and var2 will be the same size, but what they point to will not necessarily be the same size.
So it gets a little more complicated now when we're talking about the reference data type. Again, values and operations. So the values of a reference data type, well, that actually depends on the value of the data type that we're referencing. And the same goes with the operations. The operations that will be possible on those values depends on what we are referencing.
Some of the operations that are available on the underlying type might not be available in the reference if there were qualifiers on the reference, such as a const.
So now let's get a little bit more specific. We kind of shy away from just referring to something as a reference data type. It's not specific. It doesn't tell me what you're talking about. We actually need to know what kind of reference data type. There's an L value reference, a const reference, and an R value reference. Now, if you've noticed in the const reference, it really is a const L value reference. And most people drop that L value because it is implied. And it's kind of like everybody knows that you actually mean a const L value reference.
There is actually the possibility to use a data type of const R value reference, but it's almost never useful. And it's only a value in some very odd corner cases. So these are the three types of references that you need to be conscious of when you're programming in C++.
Let's look at them just a little bit closer. So when we're talking about an L value reference, we need to know the data type of what we're referencing. And there is a single ampersand before the variable. So in this example, we actually have int ampersand count B equals count A. The way it should actually be said is that the variable count B is bound to count A. That means if you modify the value of count B, this will actually change the value of count A. And you can observe the change whether you're looking at count B or count A. This changes slightly when we're talking about a const reference. Again, we have the type and a single ampersand. Count B is again a variable, and it's bound to count A. Modifying the value of count B is no longer permitted because it's const. What people sometimes forget is that you can still modify the value of count A. Nothing's changed with count A. And if you change count A, this will actually be visible by count B.
So this is a point that people often miss. The const on count B does not mean count B will not change. It just means count B cannot be used to change the value that's in count A.
So the last one we have here is the R value reference. Again, we're specifying the type, and now we need two ampersands. Count B is again a variable, and again, it is bound to count A. Modifying the value of count B will change the value of count A. Notice we're using std move. So we are going to move the value of count A into count B. The thing you have to be aware of is once you've done the move, you never want to observe count A. You don't want to access it, and you need to leave it alone. It's sort of like it's off limits. It could be valid, but don't ever count on it. Just treat it that count A is gone, and now you have count B. We want to migrate now into talking about value categories.
And there are 5 main groups of value categories: the GL, the PR, the X, the L, and the R value. You don't need to know all 5 of those, however, to reason through your code. What you need to be aware of is that every expression in your program is either an L value or an R value. And in order to determine which one of these categories it falls into, you can ask 3 questions. If any of these are true, it's an L value. If none of them are true, it's an R value. So the first question is, does this item have an identity? And the definition of this is a little abstract, but you can think of it as, is this object different from any other object in the program? For example, the number 5. Well, every number 5 is the same, so 5 doesn't have an identity. Then you ask, does it have a name? Have you given this value a name? And thirdly, you ask, does this value reside at some location in memory? Is it guaranteed to have a home in memory somewhere? If any of these are true, it's an L value.
So let's take a look at some examples. So in this very first one, the widget star button equals new widget. Button is an L value, so that's its category. The data type of button is a pointer to a widget. And again, we're very particular. It actually is a pointer to a widget. Star button is an L value, and its data type is a widget. And you actually do need to be careful because you can see the data type of button and star button are different.
So let's look a little closer at this, because you can see button is an L value. It easily passes the does it have a name test. Its name is button. We can see it. But star button does not have a name. However, it refers to an object which is guaranteed to be in memory somewhere. We know it's in memory because it has an address. We know it has an address because there's a pointer to it. So it is an L value, and its data type is widget.
So when we're looking at an R value, so we're passing this value, And result actually is, well, I should say that result is the L value because it has a name. The thing that we're passing to some function, that's the information in purple. That's the R value. So we wanted to be careful here that the result is an L value, the purple is an R value. And the R value has a data type, and that is std string.
Now the question is, why is this object that's highlighted in purple an R value? Well, it clearly doesn't have a name. It's just some string object that you have in your program. It doesn't have a memory address because it's a temporary object. It doesn't actually technically live anywhere. If you were to try to take the address of it, it would be meaningless. And it doesn't have an identity because any string that contained the characters emBO would be indistinguishable from any other string that contained the characters emBO. So this value is an R value.
So now let's take what we have and start combining everything together because we are getting closer to parameter passing. But first we need to talk about an expression. So now an expression is the combination of a data type and a value category. And remember, a data type are the values and the operations. So why an expression is important is the evaluation of an expression always generates a result. And it is the only thing in C++ that does generate a result. So let's start to look at the line of sum equals at line 2, where sum equals 10 plus 20. 10 has a data type. It is an int. It has a value category, and that's an R value. 20, exactly the same, a data type of an int, a value category. The sum of 10 and 20 is 30. That also has a data type and a value category. So 10, 20, and 30 are all expressions. What gets interesting is the variable sum, which has a data type of an int, and it has a value category of an L value. It's also an expression. So there's actually 4 different expressions in line 2.
Then the overall expression in line 2 of sum equals 10 plus 20 also has a data type. It is int, and it also has a value category of L value. Now if we look at line 3, we're using the keyword auto to declare index, and we're using whatever is returned by getIndex to determine the data type. Note that the data type of index is not auto. Auto is not a data type. Auto is a placeholder for a data type. So index has some specific data type. We just can't know what it is from this code. On the following line, index is an expression. It has an L value category. But plus plus index is also an expression. It will return some value and have some value category. But we don't know what those are because we don't know the data type of index itself.
So it would be really good to be able to decipher what the value category and what getIndex, what data type it's going to return. So let's take a look at that. GetIndex is what is called a function call expression. And what's very interesting is the value category actually depends on the return type. And you would need to see the additional code for getIndex to know what the value category is. And as you can see, what we've noted is it's normally going to be an R value. We've noted that if it returns by value, it's really a PR value, which is an R value. And on the last line, we're saying it's really an X value, which is an R value. But the value category for getIndex, if the return is an L value reference, then the category is an L value. Now, this probably already sounds a bit confusing, and it might be. But the takeaway on this slide is to understand that you can't just assume that getIndex, since it is a function call and it doesn't have a name of itself, it would look like it's always an R value. And that's not true. So its value category could be an L value. It really depends on the underlying code.
So once you can point to every expression in your source code, you will understand your code a lot better. If you can point to every expression in your source code and know what data type and value category corresponds to it, you will really understand your code.
So now let's get to the fun parts. If you were a programmer in C, or you know C at all, oh, we have a question that I should be asked. And does the evaluation of a void function generate a result? Go for it.
That is a fantastic question. And the answer is formally yes. It generates a void result. Because void is a data type, it has one possible value, which is nothing. And so evaluating a void function returns a void, which kind of sounds weird, but that is what it is. There's actually some proposals to improve the handling of void in the standard and make this a little easier to deal with, but formally it does return a result.
Cool. Okay, let me go back to the slide. Okay. So yes, if you were a programmer in C, you've heard the idea of pass by value. And pass by value is the idea that I want to pass a piece of data from a caller to some called function. And we're going to use the word function, and function could be a method or a function. In C++, we can pass by value or pass by reference. Both of these exist. Our opinion is we're saying this backwards, and it's extremely misleading. And Ansel and I do pair programming when we're working on Copper Spice, and it gets confusing for us to say, are we passing by value, passing by reference? We also have to be concerned, since we're a third-party library, how are we going to set up the API? But again, it's misleading. The idea shouldn't really be pass by. It should be receive by, because this notion of the value or the reference, it is from the perspective of the called function, not the caller. And we're going to take a look at several different examples because this got very interesting for us. I do want to mention, when we were running through these examples and we were generating this information for the slide deck, there were a few situations that actually surprised both of us on how parameters are received. So we're going to start by establishing an int data type. There's nothing really special here. It's just that we're saying that we have an int, and we're saying that it's stored at memory location 1000, and the value at location 1000 would be 27. So now we're going to take this, and we're given the exact same int we had. We're going to take the variable day A, and we're going to pass it to myfunc. As you can see in the receiving of myfunc, we have an X that's highlighted in yellow, and that's what's going to follow on the rest of these slides. The question is, what are the options that we could use for X that would be valid code? So again, the question is, are we passing by value or passing by reference? We want to change it. This X is, are we receiving by value, receiving by reference? The first two of these in the chart, and we're showing both the const and the non-const. The first two of these should be fairly simple to read. This is saying that the API wants us to pass by value, which makes perfect sense. Day A is the value 27. The second two are receive by reference. And the value 27, if we receive by reference, then we would have a reference to the 27. This one, like I said, this example, not particularly that complicated, but it establishes the foundation that you have to read the API, and the API could specify any of the four of these. And you want to know, well, what data should I be passing in myfunc? All of these work.
Now let's look at an example where we pass the address of day A. Well, if you take the address of something, you get a pointer to that object. So now we're passing a pointer to an int. So all of the options that we have for X need to receive a pointer. So they all have exactly one star in their data type declaration. But now we have a lot more options. The first two are still passing by value, or rather receiving by value.
But they are receiving a pointer by value.
The last four are receiving a pointer by reference. Now we have our options of whether we want to const qualify the pointer and or the reference. I'll call your attention to the third line in this table. Const can now appear in two different places in this data type because there are two levels at which we can qualify the data type. The first const means that the int it points to can't change. So we wouldn't be able to change the 27 that's stored in day A. The second const means that the pointer which is being passed cannot be changed. So we couldn't change it to point to a different int. The reason we have four possibilities here for pass by reference is that we now have the combination. We can have two consts. We can have const or non-const on the int, and we can have const or non-const on the reference. However, the address of an object does not have a name. The address of an object does not have an identity, and the address of an object is not unique. So we can't receive it as an L value reference because the address of an object is not an L value. The options we have are to receive it by const reference or by R value reference.
This slide is very interesting, and it shows how complicated everything can get. But it should also demonstrate why knowing expressions and value categories is extremely important. I'm not particularly saying that if I saw the very last one, the int star ampersand ampersand day B, I would be excited about that API. But I should be able to reason through that I'm seeing what exactly I'm seeing by the stars and the ampersands. I should be able to understand that I can pass an R value. And that really is some of the point of this, is to see some of the cases and to be able to decipher if the API says this, what can I pass? If you're just using an API, you can now see that you have options. Let's take a look at the next one. If we try to pass myfunc and dereference day A, well, this is one that doesn't compile because you can't actually dereference this. You don't actually get dereferencing an int doesn't actually compile or make sense. So there's no permutation here that would work in an API for what X could be.
Now let's make our data declaration a little more complex.
Let's talk about a pointer data type. So in this example, we're now having an int star month A. And just to elaborate, that what we have is that month A is at memory address 1000, which will contain the address of where the data is. And new int 3 does generate the value 3, and it will be located at memory address 5000.
Just assume that on our computer, the stack starts at 1000 and the heap starts at 5000.
Yes. So taking that same information, now we're going to go back and do the same thing. Let's look at if we just pass the value of month A, which is a pointer.
So again, the first two in this table, we are receiving a pointer by value. So those haven't changed from the last time we were dealing with a pointer data type. However, month A is a variable. It has a name. So now we're receiving an L value that is a pointer. Mm-hmm. So we have three options for how we want to receive it by reference. If we take a const reference, we can choose to receive a const pointer or a non-const pointer. However, if we want to receive an L value reference, which we can do because the value is an L value, We cannot const qualify the pointer because that would be a type conversion and would require creating a temporary.
Okay. So now let's look at this one. And yes, it gets even longer. So now what we're passing on myfunc is the address of month A. And month A is a pointer to an int. So that's what the address is. And now we're dealing with X needs to be back to some kind of pointer. And it gets really complicated really fast. And keep in mind, if you're a developer of a library or you're developing some API within your projects at your company, you could use any of these. Caution that you may want to be careful. Maybe these are a little hard to reason about, and especially line 4 that has a lot of consts on it.
So if you look at this for a moment, you can see that the data type of month A is pointer to int. So when we take the address of month A, well, we're taking the address of a thing which is already a pointer. So we're going to have a pointer to an int. And you can see that every entry in our table has exactly 2 stars, because that needs to be true for the data type to be compatible. The first 3 entries are receiving a pointer by value. And we can add const at various levels depending upon what rights we want to modify the caller's value. Then we have 5 different options for how we want to receive by reference. We can receive this pointer by either const reference or R value reference. There is no L value reference in this table because the thing which is being passed has a value category of R value, so that would never be allowed. And there are various places we can add the const qualifier based on the exact rules for conversion and type promotion of the language. But the fundamental thing to see is we still have a case where we're passing an R value and we can receive it by value, by const reference, or by R value reference. That hasn't changed. It's just the data types and the opportunities have become more complex.
And we have a clicker. There we go. Okay. So in this next example, we're now going back and we're passing star month A. So we're going to dereference this pointer. And this looks very similar to one of the first slides that we had for X. The first 2 were receiving by value or receiving by reference. And again, this is an L value reference. And it really does matter when we talk about what the value category of what we're passing and the value category of what we're receiving.
So since we're passing an L value of type int, this was exactly the same as our first example, which was also passing an L value of type int. We were just accessing it differently.
Okay. So now let's take it one more level. Let's talk about the reference data type. So in this example that we're setting up, we have year A and year B. If you notice that when we declare year B, it has the same memory address as year A, because a reference to this int is a reference and it's the exact same object. So it's just 2 ways to talk about whether we're talking about year A or year B. It is the exact same object, both having a value of 2021.
So a reference is sort of a way of giving an existing memory location a new name without changing anything else.
So in this example, we're going to pass to myfunc, year B. And let's take a look again at what X can be. This slide should start to look very similar. The first 2 by value. And again, people would say this is passed by value, but it's received by value. And the second 2 are receiving by reference. And this is an L value reference because the correlation has to be between what myfunc is passing and what the myfunc function is actually receiving.
So since we're passing an L value of type int, the answers for what the available options are is exactly the same as every other L value of type int.
So now in year B, we're taking the address and we're passing that to myfunc. These are the options that become available here. And again, X would be what you see in the API. X is the data type.
Since we're taking the address of a reference, and a reference is just a new name for the original object, that's the same as taking the address of the original object. And we already looked at an example like this. The address of an object is an R value. It's a pointer to that object. So the result of the options that are available here are exactly the same as the previous example where we were taking the address of an int.
And once again, we run into the problem that if we're trying to dereference year B, which is a reference to an int, this is something that doesn't compile and you can't do it.
Because the operations that are supported on a reference are always the operations that are supported on the underlying type or possibly a subset. There's no dereference operation on an int. So there's no dereference operation on a reference to an int, which is a really confusing piece of terminology because it sounds like you should be able to dereference a reference, but you can't. You dereference a pointer. You just use a reference. This is a really unfortunate bit of language that we've inherited from the way people talked about pointers in C.
So we want to go back now and show a couple more examples and look at this a little bit more in depth, because the idea of a reference to a pointer sounds extremely confusing. In this example, we're going to declare a widget. And then what we're going to do is we're going to declare a widget star button. And we're going to assign it to a null pointer. We're going to call show dialog. And in our show dialog, as you can see, the data type in show dialog is widget star ampersand. And this is received by reference. But the star ampersand is actually a reference to a pointer. The idea of this code is that we're going to run the dialog. If the dialog fails, we just return false. If the dialog succeeds, we're going to do something and return true. Ultimately, we're then going to be able to print what the user clicked, whether it was email, print, or cancel. A little bit of a contrived example. But what it really shows is the way that we are receiving the parameter and the way that the show dialog has the ability to update a pointer by reference.
So on the second to last line of show dialog, just before we return true, what's going to happen is we call getSelectedButton. Now, if we think about the data types and value categories of each expression in the program, we can say, okay, well, getSelectedButton must return a pointer to a widget. That value that it's returning might be an L value or it might be an R value, depending upon how it's qualified. But regardless of how it's qualified, that pointer to widget will be stored in pushButton. Since pushButton is a reference to a pointer, it's the same as if we were using the original pointer, the pointer named button in the calling scope. So we're going to update the value of button to point to correspond to the value that was returned by getSelectedButton. If we then change this, there are a couple of consequences to the fact that we've used a reference to a pointer in this example. And one of them is, in the call to show dialog up at the top, we have to pass a variable that has data type pointer to widget, and that thing that is being passed must be an L value. So it has to be something that has a name.
In this example now, we're changing, and this is a pointer to a pointer. So if you look on the line on show dialog, this is receiving by value. What gets confusing about this is you see 2 stars. You don't see an ampersand. So you might think, well, is this passed by value or passed by reference, or received by value, received by reference? But the question is, What is it we're sending and what is it we're receiving? That's the whole point of this conversation, is to correlate the two so you can reason about your code. So in this show dialog, we are taking the address of button, and then the 2 stars indicate the received by value.
Now, if you look at the second to last line here, we're still calling getSelectedButton. It's still going to return a pointer to a widget. On the left-hand side of the assignment, we're dereferencing pushButton to get access to whatever pushButton points to, which is going to be the variable button. We are then going to assign the widget pointer to that location. So in this case, dereferencing pushButton is going to give us an L value of type widget star, because what we have is a pointer to a pointer. When we dereference it, we get a pointer. That thing it's pointing to must be an L value because it has an address. Now, there's a subtle difference in semantics between these two slides, because if we go back to here, we are receiving a pointer by L value reference, which means the thing that is passed must be an L value. Here, we are receiving a pointer to a pointer, and we're not specifying what the value category needs to be. So it is possible to pass a null pointer to show dialog now. It is also possible to pass a temporary, which may or may not be what you want depending upon your application.
Because if you are receiving by value, then that value can be an R value or an L value. Okay. So we're at the summary of what we have. And this slide is what sums up everything we've really talked about. If we're passing by value, this should have been thought of as received by value. If we're passing by reference, that is received by reference. In the received by value, the value category for the argument which is being passed, well, this is the L value or the R value. And if it's an L value, remember, it's going to be copied. If it's an R value, the data will actually be moved.
So if you have a receive by value, it will accept either value category and do something different in each case. If you're receiving by reference, it's more complex to understand the meaning of the code because the required value category varies depending on the qualifiers you put on the reference. If you're receiving by L value reference, then the thing which is passed to you must be an L value. If you're receiving by const reference, then the thing which is being passed can be either value category. And if you're receiving by R value reference, the thing you're receiving must have been an R value. And this is an important point to keep in mind when you're designing an API. What value categories do I want to permit the user to pass to me? Because this turns out to be very important for making sure that all the use cases you want to support are valid and the ones you do not want to support are disallowed at compile time.
Does anybody have any questions on any particular slide? I actually have a window open to the chat that I can see, and just curious if there's anything that somebody would like us to go over again or review. We allotted some extra time at the end for questions, and we can open that up at this point and review it.
Let's give people a minute to type their questions and let's
something else. So just to let everybody know, Ansel and I have a YouTube channel with our Copper Spies project. And we, as of a week ago, we just uploaded our 60th video. So we're quite proud of that. Most of the videos are about C++. There's a few that are about Copper Spice and some that are about DoxyPress. We've recently done a series on the memory model and atomics. And if you are interested in one of our libraries, CS libguarded, that is a recent video we've just put up. Please subscribe. Please tell your colleagues. And And watch this. Oh, good. We have some questions. How do you decide what kind of passing to allow? So this is the question: is how do you decide?
So
excellent question.
Yeah. And it really comes down to this. It's what value categories do you want to permit to be passed to your function? There's a lot of rules of thumb that people use. There's no like definitive answer because it really depends on what you're doing. In general, if you're going to actually save the value that somebody's passing to you, you should receive by value. Because then, if a copy needs to be made, it will. If not, then a move will occur. It's very common to receive something by const reference because then you can accept any value category. That's just saying, I'm going to use this value. I don't care what value category it is, and I'll never look at it again after this function is done executing. L-value reference really communicates an intent. You must pass something to me that is an L value because I will be modifying it and you should look at the result. And receiving by R value means you must pass something to me that you are finished using because I will modify it in some way and damage it, and you shouldn't ever look at it again.
One of the other considerations, originally, when people first started looking at these value categories, there was the thought of, okay, we're going to change everything. We're never going to pass by value, always by reference. And it turns out that's not always the most effective way. So don't just walk through all of your code and say, that's it, no values. A lot of times, it actually is cost effective to have something being passed by value, or I should say, received by value. We're about to change the way we actually word that in the office. It takes a while to break a bad habit. So you may have to do a timing study. You may have to look at it. Although we did show several examples with lots of stars, lots of ampersands. We are not going to go back in CopperSpice and just change every API to look like that because it is harder to read because then you have to say, well, I have 2 stars, 3 ampersands, and 4 consts. What is the value category? We do want to keep it simple, but I think these charts are what are going to allow us to reason through the code because there are times I want you to change that pointer or I want you to be able to change that data. And this is what allows you to decide what is it the user is going to send me? What do I want to receive? And it's got to be decided on a per case basis. I do know one of the considerations we have in CopperSpice is that when we are setting up a method, we try to look at what the standard library did so that we try to stay somewhat consistent. But that doesn't always work for us, or it doesn't always work for the existing API of what we want to do. But that may be another rule of thumb to look at is what do we think users would expect, or what kind of data would they have in their class already or their application.
But always keep in mind the idea that it's not just about efficiency. People look at references and say, oh, well, passing a reference is faster than passing a value. Well, okay, that may or may not be true, especially now that we have move semantics in the language. But that's also not what's the most important thing in most cases, because you're actually making a conscious API decision about what you want to accept. It's not just about performance.
Let's see. What else? Is there anybody that has... I'm just sitting here reading to see if anybody has any questions. We weren't sure how difficult some of these slides were going to be. So like I said, we allowed some extra time. And thank you, Odin. We're glad that this was good for you and good for the conference. Like I said, thank you so much for emBO, to the whole conference, to everybody for allowing us to present. We just wish we could be there, and I'm sure everybody wishes they could be at the conference. If you're interested in talking to us about CopperSpice or about the libraries or any work that we've done, again, it's all on GitHub. You can download all of our source. And if you want to download binaries, those are also available. We're very friendly to work with. Please join us. Follow us on Twitter and we'll be here the rest of the conference. So if you have any other questions that come up, let us know. With the permission of the conference, we will make this slide deck available from our Copper Spice website, so that if this is a slide deck you want to hold onto, we'll upload a PDF later in the day. It's still early in the day for us here in San Francisco, so we have plenty of time. So thank you so much. And that, I guess, concludes our talk, unless there's new questions.
I think what we're going to do is we're going to go head out to the lobby,
Yes.
so as not to get in the way of the next person who's setting up in this room.
Mm-hmm.
And we'll be happy to address any questions that you would that you might have. Also, if you think of a great one tomorrow that you wish you had asked, feel free to send us a tweet or an email.
Thank you.